Hello and welcome back to Learn Along series. We are currently doing NLP with deep learning. Uh, the last two lectures we did, we got to know a little bit about self-attention transformer, a little bit of introduction into Elmo, BERT. Uh, Specifically, last lecture we had the author of Attention is All You Need paper. Uh, but I realized they, or at least I felt that they kind of skipped through a whole lot of concepts or just like the overall understanding of how do you achieve, at least from a code perspective. It was mostly an overview. uh, so I thought today we'll do another working session where we are uh, basically sort of coding side by side. If there's anything available on the internet where somebody's building the entire attention model uh, through in PyTorch from scratch. So I found something. I'm not sure how well this will be, but let's give it a shot. Let's try to um, understand the paper while we are building the code. So I will have my uh, Google Chrome, sorry, Google Colab notebook open on the side, and then uh, I'll be showing you whatever the video is. You can code side by side, or um, uh, just watch the video. Probably the person may also have provided their final code. I'll have to see, but I think I already have that link in the description of the particular website, so you can either just access that video um, in the future. So with that, I'll switch to that code, or sorry, the video. Just realized I was muted. uh, so we do have the GitHub of not sure if this just directly has the code or not, but I don't know why this is not working. Okay, let's see. Do we have the file in the GitHub? Machine learning connection. I mean, I think it's just a generic. I see. So probably not the code. But yeah, never mind. We are building that side by side anyway. So what I'll do is now on this side. Oops. Just open up my OLAP file. Wow, this is still loading. What the heck?
The original paper, Attention is All You Need, which is one of the most impactful papers in deep learning and natural language processing. Let's roll that intro and then let's get started. What is going on, guys? Hope you're doing awesome. So we're going to start with taking a look at the paper and getting an understanding of what we're going to do. And I'm going to try to explain the relevant parts. And I do think when we step through the code, it's going to help with the understanding as well. But if you still have questions about how transformers work, and then I recommend this blog post by Peter Bloom. And it's one of the resources I use to gain a better understanding of transformers. So with that said, let's start with taking a look at the paper. So the paper is Attention is All You Need. And as I said, it's one of the most impactful paper in deep learning and especially for natural language processing. So we're just going to go down to the overview of the transformer here. And if this is the first time that you see the transformer network, this is going to feel very scary. At least it did for me. And it's going to look like some stuff from the Matrix that you can never understand. But trust me, we're going to try to go through it step by step. So the first thing is that, we have to the left here, we have a encoder, all right? And then we have a decoder to the right. So hopefully you have a understanding of sequence to sequence and sequence to sequence with attention. And if not, I've made previous videos on those. But, this right here is the encoder. And so starting from the bottom, we have some input. Let's say it's some source text. And we, so for machine translation, we're going to create some embeddings. And then that's going to be sent into this block right here. All right. And we're going to call this block the transformer block. Okay. So let's just restrict our attention to just this block right here. What we can see first is that the input is going to be sent into some multi-headed attention. Okay. And this multi-headed attention, this smaller block inside this transformer block is perhaps, it is the most difficult part, and it's the essential core of the transformer, all right? So if we understand this, everything else is going to be easy. So what we can see first is that we have some input, and what this is going to do is going to send into 3 different inputs to the multi-headed attention. We're going to call these the values, the keys, and the queries. All right, for the first one, as we just have one input here, it's going to be the same input for all 3 of those. So we're just going to, repeat it and send the same input for all 3 of these value, key, and query. All right, we're going to go through the multi-headed attention in more detail, but this is sort of just the overview in that's the most important part. And then what's going to happen is it's just going to go through a normalization. Then it's going to go through a feed-forward network, and then it's going to go through another normalization. All right. These 3 parts are very easy to understand. And I think it's going to be clear as well when we go through the code. All right, so that's sort of the understanding part of what we're going to do here. Then there's these arrows here, which, if you're familiar with ResNet, these are just skip connections, so that we have our input here, which is sent through a multi-headed attention, and then the output from that is going to be sent to this norm, this normalization right here. But we're also going to take this skip connection from the previous, so the input before the multi-headed attention, and that's also going to be sent into the normalization. So just like ResNets, we're going to add them together. And similarly, this arrow right here is also a skip connection. So before we run it through the feed forward, we're going to take the input to the feed forward, we're going to send it through with the skip connection to the normalization, and then we're also going to add it with the output from the feed forward network. All right, so that's the transformer block, and we're going to go through the attention part in more detail, and also the feed forward part, but again, this is easy. This multi-headed attention is the difficult part. And then for the decoder right here, we can see first of all that the output from the encoder is sent as input. So if you remember, these are the values, keys, and queries. So the output from the encoder is going to be sent into some multi-headed attention here for the values and the keys, and then the queries here for the multi-headed attention is going to be sent from the previous part of the decoder. But let's look again. So we have let's call it a decoder block right here. And what it uses is, first of all, right here, it's the transformer block. This is the exact same part as we saw in the encoder, right? The only thing that's changed here is that we have now different inputs to the attention here, where two of them are from the previous encoder and one of them is from the previous part of the decoder. So what we can say is that the decoder block right here is this transformer block, and it has two additional ones, so the normalization and another attention. So this is pretty much the same here. We have the embedding for the output, and then we send it into this attention right here. We're gonna again send the same thing through everything, like the value, key, and query. And then we're going to have the skip connection again to normalization. And then this skip connection right here is going to come from this previous part here. And the values and keys come from the output from the encoder. And then the query here comes from this part. And then we're going to send it through a transformer block. And then finally, we're going to send it through some linear and some softmax. All right. So before we go through the attention part in a little bit more detail. First of all, we have this NX right here, which is this block, which we call the decoder block, is going to be repeated a couple of times. All right. And similarly for the encoder. So, instead of having just one of these blocks and then send that output through the decoder, we're going to do that. This block right here is going to be, the output from this block is going to be sent to another identical of these blocks, and then for a couple of times, the couple of layers, and then the output from that final block will be sent to the decoder. All right, that's just what the NX stands for here. So we repeat this for a couple of times, couple of layers, and then I guess the only thing we didn't talk about here is that so this positional encoding. The transformer network is permutationally invariant. So if you have a sentence and you change the order of the words, that means that the transformer will be invariant to those changes. It's going to be the exact same output even if you change the order of the words, which is not good, right? Because if you change the order of a few words, that can entirely change the meaning of the sentence. So we have these positional encodings, and this is sort of like an embedding that we add to the input embedding so that it becomes aware of the positions of the words. And we're going to implement a variant that's a little bit easier than they did in the paper. We're going to use positional embeddings, and we're going to go through that more when we go through the implementation. But I think, so there's one more thing in that this attention right here is a masked multi-head attention. So let's just step back a little to understand this masking. So the thing about transformers that made them so great is the fact that all operations are able to be done in parallel, which is in contrast to sequence models like LSTMs, GRUs, and RNNs. But this really big strength has one problem, which is if we look at translation where we have a target translated text, this translated text is all sent into the decoder at the same time. So, let's just say that the first element is a start token, and then the next element is the first translated word. And then the first output that we want from the decoder just corresponds to the second element which we send in the target sentence. So if we allow the encoder to have all this information, this is going to be super easy. So it will just learn to use the provided target translation, and it will just learn a simple mapping and really not learn anything about translating text. So what we do is that we mask the target input to the decoder so that the first output of the decoder only had access to the first element. And then the second output only had access to the first and second input to the decoder. Now that we have an overview, let's try to take a deeper look at the attention mechanism. So the absolute first thing we're going to do is we're going to take the embedding input, and let's say it's 256 dimensions, and we're going to split it into several parts. So let's say we split into 8 parts. Now 8 of these parts all have 32 dimensions each, and they're all going to be sent in through linear layers. And that's also why we have these linear shadowed parts here, is because we are sending in the input which has been split. And then we send the output from those into this scaled dot product attention. All right. And they have a figure here, but I think the formula is a little bit clearer. So essentially the scaled dot product attention is that we take the queries and we multiply them with the keys. Then we do a scaling, which is that we divide by the square root of the embedding size. Essentially, this is just for numerical stability. Then we do a softmax of that. And lastly, we multiply it with the values. Okay, that's the scaled dot product attention. So what we do then is that we concatenate all of those different parts that we split, so that we obtain the same as the input, so the embedding size. And then that is then sent through a linear layer, and that's the output from the multi-headed attention. Now that we have a basic understanding of the transformer network, we're ready to start coding. So there are a bunch of things I didn't mention in the implementation details, and I'm gonna sort of talk about them as we go through it. But I think the necessary understanding is there for us to start coding it. So what we're going to do first is we're going to do, as usual, import torch. We're going to do import torch.nn as nn. And the thing we're going to start with, which is perhaps the most complicated thing, is self-attention. So we're going to do class self-attention. We're going to do inherit from nn module. And we're going to do define init. And we're going to send in the embed size, and we're also going to send in heads. So as I said, we have an embedding, and we're going to split this embedding into different parts. I believe I said 8 different parts. And in that case, how many parts we split it is what we're going to call heads. So if we have, for example, embed size 256 and we have heads 8, then we're going to split it into 8 by 32 parts. So we're going to do call super.
Yeah, I gotta understand this part again.
We're going to do import torch.nn as nn. And the thing we're going to start with, which is perhaps the most complicated thing, is self-attention. So we're going to do class self-attention. We're going to do inherit from nn module. And we're going to do define init. And we're going to send in the embed size. And we're also going to send in heads. So as I said, we have an embedding, And we're going to split this embedding into different parts. I believe I said 8 different parts. And in that case, how many parts we split it is what we're going to call heads. So if we have, for example, embed size 256 and we have heads 8, then we're going to split it into 8 by 32 parts. So we're going to call super first, self-attention, and we're going to do self, and we're going to do dot init. So we're going to initialize the parent class, and then we're going to do self.embed size equals embed size. We're going to do self.heads equals heads, and self.head dimension equals embed size, integer division by heads. All right, so let's say that we want to split it. We have 256 embedding size and we want to split it into 7 parts. Then that would not be possible since we can't make an integer division of that. So what we can do is we can throw out an assert. We can say assert self dot. We can do it like this: self dot head dimension times heads equals embed size. And if it doesn't, we can say embed size needs to be divisible by heads. What we're going to do then is we're going to define the linear layers that we're going to send our values, keys, and queries through. So we can do self.values is nn.linear, and it's just going to take the head dimension and it's going to map it to the head dimension. And we're going to set bias equals false. And then we're going to do self.keys is equal to nn.linear. And we're going to do head dimension times heads equals embed size. And if it doesn't, we can say embed size needs to be divisible by heads. What we're going to do then is we're going to define the linear layers that we're going to send our values, keys, and queries through. So we can do self.values is nn.linear, and it's just going to take the head dimension and it's going to map it to the head dimension. And we're going to set bias equals false. And then we're going to do self.keys is equal to nn.linear. And we're going to do self.head dimension. And I guess same thing. Could have just copied that. Could have copied it again. But anyways, queries nn.linear, self.head dimension to self.head dimension. Again, bias equals false. And then we're going to do, after we concatenate, we're going to do fully connected out. It's going to be nn linear of heads times self.head dimension and then the embed size. I guess, yeah, so we don't have to write it like that, I guess, since the heads times the self-head dimension needs to be equal to the embed size. But yeah, maybe this makes it a little bit clearer that we're going to concatenate them. And then we're going to do the forward. And we're going to send in the values, keys, query, and we're also going to send in a mask. So the first thing we're going to do is we're going to get the number of training examples. So n, we're going to set to query.shape of 0, and that's going to be how many examples we send in at the same time. Then we're going to do the value length, the key length, and the query length. And remember, the value and I guess those lengths are going to, depending on where we use the attention mechanism, is going to be corresponding to the source sentence length and the target sentence length. But since we don't know exactly where this mechanism is used, either in the encoder or which part in the decoder, those are going to vary. So we just use the abstract of saying, we just use it abstractly and say value length, key length, and query length, but really they will always correspond to the source sentence length and the target sentence length. That's just one thing to keep in mind. And then we're just going to do values.shape of 1, keys.shape of 1, and then query shape of 1. And that's just where they're going to be in the dimensions. So what we want to do now is we want to split embedding into self.heads pieces. So we're going to do values is values.reshape, and then we have n comma value length comma self.heads comma self.head dimension. So these two right here is where we're splitting it. Since this was before a single dimension of just embed size, now it's going to be self.heads and then self.head dimension. And we're going to do the same thing for the keys. So keys.reshape, we're going to do n key length, self.heads, and then self.head dimension. Moving along to the queries, we're going to do pretty much the same thing. Query.reshape, n key length, self.heads, and then self.head dimension. And then what we're going to do is we want to multiply the queries with the keys. And so we're going to call the output from that energy. And what I'm going to use is maybe something that you're not familiar with, but it's torch.einsum. And I'll explain what it does, but essentially we're going to use it for matrix multiplication where we have several other dimensions. So let's just bring out the shapes first. We have queries. So queries shape is moving along to the queries. We're going to do pretty much the same thing. Query.reshape, n key length, self.heads.
Shouldn't this be query length rather than key length? I don't know.
And then self.head dimension. And then what we're going to do is we want to multiply the queries with the keys. And so we're going to call the output from that energy. And what I'm going to use is maybe something that you're not familiar with, but it's torch.einsum. And I'll explain what it does, but essentially we're going to use it for matrix multiplication where we have several other dimensions. So let's just bring out the shapes first. We have queries. So queries shape is n comma query length comma heads dimension. And then we have keys shape, and I guess pretty much the same, n comma key length heads dimension. And so what we want, so we energy is going to be n comma heads comma query length comma key length. All right, so you can kind of view this as let's say the query length is the target source sentence, and the key length is the source sentence. Then this will kind of say that, okay, for each word in our target, how much should we pay attention to each word in our input in the source sentence. And what we want here anyways for the matrix multiplication is that we want to multiply, well actually let's do this first. So let's see, right here. We're gonna do n query for the query length, h for the heads, and then d for the heads dimension. And then we're gonna do comma n k again for the key length, n for the batch size, k for the k length, and then h for the heads, and then d for the head dimension. And then we're gonna create a, let's see if I can do this. We're gonna do an arrow like this. No, not like that. Like this. And then we're gonna specify the output shape. So we still want n to be the output shape, and then we want heads to be the first one, and then we want query length, and then we want key length. All right. This einsum has quickly become sort of my favorite notation. Instead of using matrix multiply, or in this case, what you would have to do is you would have to use batch matrix multiply, since we have a batch here. And you would even have to do it a little bit more complicated, since we have this additional dimension here for the heads. You would first have to flatten the training examples with the heads, and then use torch.batch matrix multiply. So you would have to use torch.bmm. But if you don't want to remember sort of those syntax for how to do that, you can just use einsum, and it's going to be super easy. And what we have to do here as well is that we need to send in the queries and then the keys. And that's it. We're going to add a mask now. So we're going to do if mask is not none. So if we send in a mask, then we're going to do energy equals energy dot masked underscore fill. And then we're going to do mask equals 0. So essentially, if the element of the mask is 0, then that means that we want to shut that off so that it doesn't impact any other. I guess, yeah. So essentially, as we saw previously, the mask for the target is going to be a triangular matrix. But we're going to define that later on. But anyways, the element that, when we're going to close it is 0. And what it means to close it is that we're going to replace those elements with a float, where we're going to set it to essentially minus infinity, but just for numerical, so it doesn't bring any numerical under or overflow or anything like that. We want it just to set it to a very, very small value. And so let's see what's going to happen is, we're going to run this through a softmax now. So when we have those essentially minus infinity, then they're going to be, set to 0. So we're going to do attention now, and we're going to do torch.softmax, and we're going to do energy, and then we're also going to divide it with the embed size, or the square root of the embed size, just for that numerical stability. So we're going to do raised to 1/2, and then we're going to do dimension equals 3. And this means that we're normalizing across the key length, which, for example, would be, depending on, again, where we use the attention mechanism, it's going to, let's say this is the source sentence and this is the target sentence length, then that would say, how much we want to, essentially we're making the attention scores normalized to 1 across the source sentence, so that if the first, for example, is 0.8, that means we're paying 80% attention to the first word in the source sentence. What we can do then is out, and we're going to now want to multiply the attention with the values. So again, we're going to use my favorite notation, einsum, and we're going to do that by, let's bring out the shapes first. So we have attention shape, we have n, comma, heads, comma, query length, comma, key length. And then we have the values shape, and we're going to have n, comma, value, length, heads, and then heads dimension. And what we want after the matrix multiply is we want it to be n, comma, query length, comma, heads, comma head dimension. All right, that's so what we want here is the key length and the value length are always going to be the same. If you just check how we are sending it in, in the encoder, they are all going to be the same. Obviously, it's just going to be the same input. We're going to see that later on as well. But the value and the key length are always going to be the same value. So we're going to multiply across that dimension. So again, we can do, we can do this right here. And we're going to call it N for the batch size, for the attention, and then heads, and then query length, and then we're just going to call it L for the dimension that we want to multiply across. Then we're going to do again N comma or I guess NL, so that's going to be for the value length, and since the key length and the value length match now, so both are L, then we're going to do H, and then we're going to do D. And we're going to map this. So let's see, we're going to do like this, and we're going to do it to N, and then the query length, heads, and then the dimension. And magically, Einstein is going to know what to do with that. So all we're going to do then is just do the attention and send in the values. And also, so we're now going to want to do the concatenation part. So we can do that. Instantly after this torch.einsum. So we can do dot reshape, and we can do n comma query length, and then we can just self.heads times self.head dimension. So we're just concatenating those. So we can do, I don't know, we can write here after einsum, then we can just do then flatten last two dimensions, something like that. And what we want to do lastly is just send it through fc out. So we're just going to do that, and we're going to return out. And this fc out won't change the dimension, since the fc out just maps the embed size to embed size. All right, so now that we have the attention, this is going to be a lot easier for us. So we're just going to create the, now we're going to, we're going to create the transformer block. So we're just going to do class transformer block, and we're going to do NN module. We're going to define init, and we're going to do the embed size. And we're going to send in the embed size, the heads dropout. And we're also going to send in something called forward expansion. And I'm going to talk about that when we use it. So we're going to do super, and we're going to do transformer block. We're going to do self, and then see dot init. And we're going to do self.attention is equal to self-attention of embed size and heads. So essentially, we're using that attention that we implemented above. And then we're going to do the normalization. So we're going to do self.norm1 is going to be, because we're going to use two normalization. We're first going to send it through a normalization, a attention block. We're then going to send it through a normalization. We're going to send it to a feed forward, and then we're going to send it to another normalization. So we can do layer norm of embed size, and layer norm, again, one of those details. So if you're familiar with batch norm, layer norm and batch norm are very similar, except that batch norm takes the average across the batch and then normalizes, whereas layer norm just takes an average for every single example. So I guess layer norm has more computation than batch norm, but essentially it uses the same formula. It just does it per example rather than for the batch. So then we're going to do another one. Self.norm2 is going to be and then layer norm of, again, the embed size. And then the feed forward part of the transformer block, we're going to do self.feedForward is going to be nn.sequential. So we're going to use a different nn linear here. And what we're going to do is we're going to do nn linear from the embed size as input. And then we're going to map it to forward expansion times the embed size. So essentially, we're mapping it to some more nodes, which is dependent on the forward expansion. So in the paper, they used forward expansion to 4. So essentially, they have the embed size, and then they just times that by 4, which is the intermediate number of nodes. They do an NN ReLU, like this. And then they use another NN linear, and they're going to do the forward expansion times the embed size, and they're just going to map it back to the embed size. So, this feed forward block is not really changing anything. It's just doing some extra computation. And then mapping it back. And then lastly, we want to do self.dropout. Self.dropout is equal to nn.dropout of dropout. And for our forward, let's see if I can make this a little bit more centered. All right, so now we can scroll past the bottom. All right, so we're gonna do the forward, and we're gonna send in, the value, the key, the query, and we're also gonna send in the mask. Then we're gonna do attention equals self.attention, and we're just gonna send in the value, key, the query, and the mask. And then, we're gonna do self.norm1. And one thing to remember is that we're gonna send in a skip connection, and that's gonna be the attention that we just computed, and we're gonna add it with the query. So that's the skip connection. Then we're gonna do self.dropout. Let's see, like this, and we're gonna do x equals that. Then we're gonna do forward equals self.feedForward of x, and then we're gonna do out equals let's do self.dropout of self.norm2, and again we're gonna add the skip connection. So we're gonna do forward, but we're also gonna add the x from the after the norm, norm1. Then we're just going to return out, and that's the transformer block. So as I said, the attention part right here is really the most difficult part. The transformer block is pretty easy, and now we're just going to try to stick this together and form the encoder and the decoder. So we're going to do class encoder, we're going to do NN module, and we're going to do define init. And we're gonna, let's see, we're gonna do self. We're gonna send in the source vocab size. Because remember, now what we're gonna do is we're gonna do the embedding and all of those things as well. And we're also gonna use the transformer block for a couple of layers. So we're gonna send in the embed size. We're gonna send in the number of layers. We're gonna send in heads. We're going to send in device. We're going to send in forward expansion, right? All of these are hyperparameters of our model. We're going to send in a dropout, and we're going to send in something called max length. And so first thing we're going to call is super of encoder self dot init. And we're just going to do self dot embed size equals embed size. And I'll cover, let's see, so I guess the only thing that we haven't talked about is max length. And this is related to the positional embedding. So essentially, we're going to use a positional embedding, and I'm going to talk more about that when we code that one. But essentially, the positional embedding is depending on position, right? And so we need to send in how long is the max sentence length. So let's say that we have a couple of sentences that are, let's say that they're extremely long. Let's say all of our data set is 50 in length, and then we have a couple of examples that are 1,000. Then what you would have to do is delete those that are 1,000 and just keep the ones so that we have sort of a normal size of our data. And so max length varies depending on data, but perhaps it's like 100 or something like that, depending on the data set. So we're just going to do self.embed size. We're going to do self.device equals device. Self.word embedding is going to be nn.embedding. We're going to send in the source vocab size, and we're going to map it to embed size. And then we're going to do the positional embedding. And this is just going to be nn.embedding, and it's going to be max length to embed size. All right, so this is where we use the max length. Then we're going to do self.layers. It's going to be nn.module list. We're just going to use that to map several different modules together, and those modules are going to be the transformer block. So we're going to do transformer block, and we're going to send in the embed size. We're going to send in heads. We're going to send in dropout equals dropout. We're going to send in forward expansion. Forward expansion equals forward expansion. And that's it for the number of layers. Let's scroll down again. And then we're just going to do self.dropout equals nn dropout of dropout. All right, so we're ready to do the forward parts. We're going to do forward self. We're going to send in just one input to the forward, and we're also going to send in a mask. Then we're just going to do n comma sequence length is x.shape. So that's all we have from the beginning, right? We have an example sent in, and we have some sequence length. And then we're just going to do, first of all, we're just going to do positions that we're going to do torch.arrange 0 to sequence length. And then we're going to do dot expand n comma sequence length, so that we have arrange, so 0, 1, 2, 3, etc. up to sequence length for every example. And then we're just going to do dot to self.device. And then we're going to send through x through an embedding, and we're also going to add a positional embedding. So self.word embedding of x plus self.position embedding of positions. And this together is then going to be sent in through dropout. So we're just going to do something like that, and we're going to do out equals that thing. And so, if you really think about it, the only thing that makes it aware of the positions is this thing right here, where all we're going to send in is the positions, which is just 0, 1, 2, 3, etc. And magically this learns how to you know, how words are structured in you know, the permutation of the words. I find that a little bit magical that actually works. But anyways, so we're gonna do for layer in self.layers. We're gonna do out equals layer of, and this is gonna be a little bit weird, but since we are in the encoder, the let's see, the value, key, and the what is it? Value, key, and query are all gonna be the same. So we're just gonna send in out, and we're also send in the mask. All right. So that's looks a bit odd, but that's just a special case in this scenario. In the encoder, all of the inputs are going to be the same. So, and then we're gonna do return out. All right. So now we have the what is it? Value, key, and query are all gonna be the same. So we're just gonna send in out, and we're also send in the mask. All right. So that's looks a bit odd, but that's just a special case in this scenario. In the encoder, all of the inputs are going to be the same. So, and then we're gonna do return out. All right, so now we have the encoder done, and all we want to do now is we want to create the decoder. And to make this, I guess, hopefully clearer, we're gonna do the decoder block first. So we're gonna do NN module. We're gonna do init. We're gonna send in the embed size, heads, forward expansion, dropout, and device. And then we're gonna do super of decoder block self dot init, like this. And so remember that the first thing we're gonna do is we're gonna send it through an attention layer. Then we're gonna do the normalization, and then we're just gonna use the transformer block. So we can do self.norm is, or let's do attention first. So self.attention is self attention of embed size, comma, heads. And then the norm is just going to be an layer norm of embed size. And then transformer block will just be transformer block of, let's see, embed size, heads, dropout, and then forward expansion. And also we're just going to do our dropout. So nn dot dropout of dropout. Now we're ready to do the forward part. So we're going to do forward, and we're going to do x. We're going to send in value and key. And then this, we're also going to send in a source mask, and we're going to send in a target mask. All right. So the target mask is the one we've talked about. And this one is I guess this one is essential. You need to have this one. The source mask is kind of option, where if we send in a couple of examples, then we need to pad it to make so that all of are equal length. And then we can also send in a source mask so that we don't do unnecessary computations for the ones that are padded. So that one is optional, but we're going to do it. And then also remember, in the decoder block, we take X, we take an input from our target, and then we also take the value and the key, and we're going to get those from the encoder that we've already run before this. So what we're going to do is we're going to do attention is just going to be self.attention of X and X, because all of those are the same. And then we're going to send in the target mask, because remember, that's the mask multi-headed attention, the first one in the decoder block. And then the query is just going to be self.dropout of self.norm of attention plus X, which is with the, with the skip connection. And then out is just going to be self.transformer block of the value, the key, and the query, and then also the source mask, which is optional, but we're going to do it. And then return out. So now we can do class of the decoder. So we're going to do class decoder, and then module. We're going to do define init. We're going to do target vocab size, embed size, num layers, heads, forward expansion, dropout, device, and also max length. Yeah, so we're gonna do it like that. This looks a little bit weird. All right, so now we can start by writing in super of decoder and self, and we're gonna do underscore init like this, and then self.device equals device. Self.word embedding is gonna be nn.embedding of target vocab size, and then the embed size. And then we're gonna do self.position embedding. It's gonna be nn.embedding of, again, max length, and then the embed size. And then self.layers, it's going to be nn.module list. And we're going to do decoder block of embed size, heads, forward expansion, dropout, and then the device. And we're going to do that for, in range of num layers. So that's going to be the layers. And then we're going to do self.fc out. It's going to be nn linear of embed size and then target vocab size. And let's see, kind of lost my track here. So we've done the layers, and then yeah, so we're just going to do the last linear layer. So now we're done with the sort of after the decoder block. That's just going to be another linear layer, and then we're just going to do it. Self.dropout is and then dropout of dropout. Then again, we're going to do forward self, and we're going to do X here for input to the decoder. And then we're going to do the encoder out. We're going to send an encoder out. And then we're going to do source mask and then target mask. And let's see here. So we're going to do n comma sequence length equals x.shape. We're going to create the positions, which are just going to be torch.arrange 0 sequence length. And then we're just going to do expand n comma sequence length so that we have it over all of the training examples. We're going to get it to CUDA if it's a bit available, and then we're just going to do x is self.dropout of self.word, let's see, self.word embedding of x, and then plus self.position embedding of positions. And then, we're just going to do for layer in self.layers. We're going to do x is layer of x, and then so that's going to be the let's see, that's going to be the value to the decoder, so the input to the decoder block, and then we're just going to send in the encoder out for the, let's see, for the value and the key. All right, so I guess we can do this. So here we have x, we have value and the key, and those are going to be the same thing, which is output from the encoder. So let's see. Here we're going to do, also we're going to send in, let's see, the source mask and then the target mask. And then out is just going to be self.fully connected out of x. So we're going to get a prediction of which word is next, which is going to be dependent on our vocabulary size for our target. All right, I think this is going to be a long video, but now we've done the encoder, we've done the decoder, and we're ready to put this together and do class transformer of nn.module, and we're gonna do some init here, and we're gonna do self. We're gonna do source vocab size. We're gonna do target vocab size. We're gonna do source pad index. We're gonna do target pad index because those are necessary to compute the mask that we're gonna use. Then the embed size, we're going to set to 512. Or actually, we can use 256 as we did. And then number of layers, we can set to 6. The forward expansion, we can set to default 4. The heads, we can set to default 8. Dropout, we can set default 0. Device, we can set default CUDA, and then max length is going to be, let's say, 100. Then we're just going to call super of transformer self dot init, and then we need to just first define the encoder. So we're going to do self.encoder is going to be the encoder, and we're just going to send in the source vocabulary size, the embed size, the number of layers, heads, device, forward expansion, dropout, and then max length. All right, that's just how we defined the input ordering of the encoder. Then we can do the same for the decoder. It's just going to be decoder, and we're going to send in the target vocabulary size, the embed size, number of layers, heads, the forward expansion, the dropout, the device, and then the max length, like that. And then we can also just, do the source pad index is source pad index, self.target pad index is target pad index, and self.device is just device. And so what we got to do first is we got to make a function to make the source mask and then the target mask. So we can do make source mask, and we're just going to send in the source, and we're going to do source mask is going to be source, and then we're going to do not equal to self.source pad index, and then we're just going to do unsqueeze 1 and then unsqueeze 2. So the and then we're going to do not equal to self.sourcePadIndex, and then we're just gonna do unsqueeze 1 and then unsqueeze 2. So the source mask is gonna be n. This is just to make the shapes add up. So we're gonna do n, 1, 1, and then the source length. That's all the shapes are gonna be, and then we're just gonna return source mask dot to self.device. So again, if it is a source pad index, then it's going to be set to 0, and if it's not, it's going to be set to 1. And that's how we defined the source mask. You can also use, I guess, the opposite, but that's just how we defined it here. And then we're going to do define make target mask, and really all we're going to do here is we're going to get the target length by target.shape, and then we're going to do target mask is going to be, we're going to do a triangular matrix. So we're going to do torch.triangular lower, and we're going to do torch.ones. So the element values on this lower triangular matrix is going to be just values of 1. And then it's going to be target length and target length. And we're just going to do another thing, which is expand it, so that we have one for each training example. And then we can just do return target mask dot to self.device. And we're also going to do define forward, and it's going to be source and target. So now we send in the source and the target, and basically, we're going to do source mask is self.make source mask of source, and then target mask is going to be self.make target mask of target. So I guess that makes sense. And then we're just going to do encode source is going to be self.encoder of source and source mask. And the decoder, or let's say out, is just going to be self.decoder of target, and then encode source, and then the source mask and the target mask. And then we're going to do return out. And yeah, so now we created the entire transformer. So what we can do is I have an example right here, and I'm gonna copy that in so we don't have to write that. But just I guess a small example, that just a toy example to see that it runs. So we have device, CUDA, and then I have some example right here. And so the 1 is for the start token, 0 is for padding, and 2 would be some end of sentence. So this is just random, and this is no data, but just as an example. And then we have 2 examples right here, and then we have some target right here, not necessarily the same shape as the input. And then we just define the source pad index. We define what is the vocabulary size. So here I use, I don't go above 10. So 9 is the maximum right here. So the source vocabulary size is 10. Then we just do model, and we do transformer of source vocabulary and then pad index. And then we just do model, and we send in X. And we also send in the target, except the target will be shifted by 1, so that it doesn't have the end of sentence token, because we want it to learn to predict the end of sentence. But I guess that's more of how you would use the transformer, and this is sort of more focus on how to actually implement it from scratch. But this would be used later on, to send to cross entropy and etc. Yeah, but not to take too much focus on that. So let's try and run this. There's probably going to be a few errors. We've written a lot of code. And yeah, so invalid syntax. We can do line 119. Yes, we're going to have to do what? We're going to do like this. And we're going to run it again. No module name torch. Oh, okay. Yeah, I remember. So I need to do, see, and the import torch error was just because I had to activate my conda environment. But then we get another error when I rerun it. So that error is because in this line right here, in line 25, for the query reshape, we use the key length, which we should use the query length right here. And let's see if this runs now. All right, so it took a little bit of time, but I found the error now. So here, this one wasn't actually causing the error, but this is an error. So we're gonna do the transformer block for a couple of layers. We're gonna do in range of num layers. Right, so it took a little bit of time, but I found the error now. So here, this one wasn't actually causing the error, but this is an error. So we're gonna do the transformer block for a couple of layers. We're gonna do in range of num layers, like that. And then what caused the error is that in the layers, like that. And then what caused the error is that in the decoder, somehow I returned, I forgot to return, so return out. Also, there was one very important thing that I missed in the self-attention, which is that after we do the reshape, we need to send them through the linear layers. So we're going to do values equals self.values of values, and then keys equals self dot keys of keys, and queries equal self dot queries of queries. And if we now run this, queries of queries. And if we now run this, we get the correct shape. And I've also tried to train this on some translation tasks, and it seems to work similarly as PyTorch own implementation. But of course, there might be some error in it that I might have missed. But so there you have it, the transformer from scratch. This was definitely a more challenging video, and definitely for me at least. So hopefully this was helpful for a couple of you, and yeah, thank you so much for watching the video.
Uh, yeah, I was expecting some sort of a. I mean, obviously you can't run a full-fledged example, but I was expecting some sort of an application to a direct example as well. But never mind. Since we have the code structure ready, I'd say I'll, in my own time, try and see if this works, or if there are more errors needs to be debugged for a standard example out there. Uh, Take like a simple sample uh, database and then uh, run on that vocabulary, try to see how that performs, and probably even run that against the earlier methods that we've seen, LSTM, GRU, and then compare and contrast the performances. But yeah, I think that's it for today. A little heavy video on the coding front, but always, I would say, good to keep on, getting down within the code as much as you can so that you are comfortable with this. But thank you for joining, and I'll see you guys tomorrow. Bye.